Namaskar, hello everyone. Today we are going to discuss about hydrogen atom. So to be specifically, the discussion is about normalized radial wave function of hydrogen atom. This topic is from the request of a student. Okay, so what we are going to discuss is we will first see what kind of system it is, right? Uh, the hydrogen atom we are going to consider it as a two particle system. So it is also, we can say this system is like ionized helium or doubly ionized lithium. Okay, so it is a two particle system. So in this case it is consisting of atomic nucleus of charge Ze and electron of charge minus e. Here Z is 1, we know that, but for a general equation we will keep the Z. Now, if the nucleus is supposed to remain static, that is, if the nucleus is not moving, then the Schrodinger equation is only and only for single electron, right, which is moving in a potential minus Z square by R. Now, see, Z square by R, this is just the electrostatic potential energy of interaction between two charges, right. So, that is the potential we are going to work with. Okay. So, when atom as a whole is at rest, what does that mean? That if the atom including the electron, here we discussed about nuclear to be remaining as static, but if entire nucleus is at rest, the center of mass mu is to be considered, right. Okay. So, the center of mass mu is given by this equation, and if the entire system is static, we consider center of mass and it also remains static. Okay. Now, the potential we saw above is spherically symmetric, and that is why we are going to discuss the radial wave equation. Okay. The radial wave equation we have already discussed in the previous videos, that is for the square well potential, three-dimensional square well potential in the exterior region and interior region. Okay. So, using that base where we consider the particle in a central potential. So, from that we derive this radial wave equation and we will begin with this equation. Okay. So, to get some reference, if you have not studied it, I suggest that you look into the derivations, how it comes, and then you can follow with the rest of this video. Okay. So, here we are going to substitute the potential, that is Z square by R, and we get this equation, that is 1 upon R square d by dr, R square dr by dr plus 2 mu upon H square E plus Z square by R minus L into L plus 1 upon R square, R of R is equal to 0. Now, we are going to consider the bound state. What does bound state mean? So, bound state means the energy E is less than 0, right. You can also look at the previous videos for the exterior region where you will understand the bound state. Okay. To rewrite the above equation, the Schrodinger equation in dimensionless form, we have to define dimensionless parameters. So, we define rho, which is equal to alpha into r, such that its dimension are nullified, that is meter inverse into meter. So, alpha has a dimension of meter inverse, and for that we define positive real parameters alpha and lambda, right, such that the value of alpha square is this and lambda is given by this equation. Now, using all this equation, right, what we are going to do is we are going to rewrite this equation of ours. Okay. So, you substitute the values and you can rewrite the equation by substituting r with rho is equal to alpha r, and since rho is equal to alpha r, my r, that is the radial component, can be written as r rho. So, my r becomes my r rho. All right. So, I leave this exercise to you where you have to write and substitute all the parameters and you will get this equation, which is alpha square by rho square into alpha into d by d rho, rho square by alpha square into alpha dr by d rho plus into the bracket 2 mu e upon h cut square plus 2 mu z square alpha divided by h cut square rho minus L into L plus 1 by rho square alpha square r of rho is equal to 0. Now, we see alpha square over here and we also see alpha square in the other equation. So, what we are going to do? We are going to divide the equation by alpha square, alright. So, by dividing so, we get this particular form in this equation, okay, simple. Then we see that it is a derivation d by d rho of u dot v form, alright. So, it is a simple derivation. So, this equation transforms into this equation, okay. Now, if you observe, then our alpha square as we define is minus 8 mu e upon h cut square. So, over here we have alpha square over here. So, if we substitute it, it transforms into minus 1 upon 4, right. And in this equation 2 mu z square upon alpha h cut square, right, it is nothing but lambda. So, it becomes lambda by rho, right, rest of the term as it is and we get this equation, okay. Rewriting all the terms, that is we rearrange the terms within the bracket, we rewrite this equation and we will give this equation some equation number 1, okay. Now, this equation we have. So, next step is to check the behavior of the radial wave function in the neighborhood of the nucleus, right. So, we want to see at the center, right, at 1s orbit we are going to look at the center, what is the behavior of the wave function. So, the value of rho is very small. So, small value of rho is there. So, as r tends to 0, we have seen in the previous case, or if you refer to the case of particle in a central potential, you will observe that in this kind of cases when r tends to 0, the acceptable solution behaves like rho to the power L, that is your radial function behaves as if it is equal to rho to the power L. So, let us look at again. So, let us say this is our nucleus, proton is there, one particle, charge is plus Ze, electron minus E, then for r is equal to 0, rho is alpha dot r, which is dimensionless quantity, is also equal to 0, and our r rho behaves as if it is a rho to the power L. Now, if we observe for the large value of rho, right, for the low values, that is r tending to 0, small values we have observed. For large value of rho, that is in the asymptotic region, as r tends to infinity, rho is equal to alpha into r also tends to infinity, right. For this particular case, the approximate radial wave equation becomes of the following form, right, that is this. Why? Because here minus 1 upon 4 is the dominant term within the bracket in this equation, right. So, in this bracket, okay, minus 1 upon 4 term becomes dominant, right. So, see, I am not deriving all the terms so that we can complete the video in a limited time frame, right. Okay. So, if you have any query and questions regarding this, I will help you and I will give the solutions and to your questions, and so please post your questions in the comment section, give your reviews as well, okay. Moving on. So, this particular form we get, and this particular equation has two solutions, that is r rho is equal to e to the power minus rho by 2 and e to the power plus rho by 2. Then for the large values, that is rho tending to infinity, for the asymptotic behavior we observe that e to the power minus infinity tends to 0 and e to the power plus infinity tends to infinity, right. That means we are going to incorporate one of the result and we are going to rewrite the equation, the radial wave component including rho to the power L and e to the power minus rho by 2 and L rho. Now, what is the L rho in this particular equation? So, L rho is some unknown polynomial, right, it is a some unknown polynomial. Now, how did I come to this point? So, see, it's a mathematical task that we have to take. To discuss this, I can take another lecture, since this is it will take it takes longer time. You have seen in the previous video, it takes very longer time to go for each and every minute detail. So, it's an unknown polynomial. What is it? We are going to see very soon. Okay, so let's continue. Substituting the values of this R row in the equation number 1, where we have R row, we have dr by d row, and we have d square r by d rho square. Okay, so substituting all these values, right, in the equation number 1, we get this particular form. Now, how did I get that? So let me write one of the differential, that is dr by d rho. Okay, so let me check. Okay, so I can look at that r rho is rho to the power l into e to the power minus rho by 2 into l rho. So my dr by d rho, what it will be? It will be rho to the power l into e to the power minus rho by 2 into d l rho by d rho plus rho to the power l into l of rho into minus rho by 2 into e to the power minus rho by 2 plus e to the power minus rho by 2 into L of rho into L into rho to the power L minus 1, right. Then you differentiate it again and you will get d to d second order differential of dr by d rho. Okay, and then you substitute all the values in equation number 1, and you follow that after substituting all these values you will get this equation. So please note it down. All right, take a pause, derive the second order differential, and then move ahead. Okay, so now we have derived the equation in this particular form, right, where we have taken the R rho as if its solution is rho to the power L into e to the power minus rho by 2 into some unknown polynomial L rho. All right, now the next part is that we want to obtain the stationary state wave function, that is of the radial wave function, right. So we have now equation number 2, and for this equation we are going to consider that lambda is some kind of integer, lambda is equal to n, which is having values from 1 to n so on, right, and it can be expressed in terms of associated Laguerre polynomial. Why? Because the equation number 2, that is this equation, is of the following form. Now if you compare, right, this is the equation of associated Laguerre polynomial differential equation. So if you compare equation number 2 with equation number 3, right, you can now easily say that our unknown polynomial L rho is nothing but associated Lagrange polynomial LQP rho. All right. Okay, fine. So now what we have to do is we are going to consider the equation in terms of associated Laguerre polynomial. Now for our equation, where we have considered lambda is an integer, so if we consider lambda to be an integer, then with p is equal to 2l plus 1 and q is equal to n plus l, okay, we are going to rewrite our LQP as L 2l plus 1 and n plus l rho. Now let's go ahead. So the next task is to find the solution. Okay, so by introducing the Laguerre polynomial, our equation change in terms of NL, right, and what happens is that my R and L rho is now represented as some constant into the rho to the power L into e raised to minus rho by 2 into Ln plus L 2L plus 1 rho. Now our unknown polynomial is nothing but Laguerre associated Laguerre polynomial, right? Okay, so this constant I can rewrite as n and L. So I just rewriting the equation for given value of n and L. Now we already have derived defined, sorry, not derived, we have defined the values of alpha. Okay, so the alpha square is given. So just rearranging the term, we see that it can be rewritten in this equation, right? And we get this particular form. So if you keep on substituting the terms, what do we get at end is 2z upon n a. So what is a over here? So a, that is h cut square upon mu e square. It's a Bohr radius. Bohr radius. Right. What is a Bohr radius? It's a smallest radius. Okay. Okay. That's enough for time. Now, okay. So now I have alpha. Now I know that my rho is equal to alpha into r, dimensionless quantity. So we substitute simply the value of r, right? And we have this value that alpha is equal to 2z upon Na into r, where a is h cut square upon mu e square, Bohr radius. Okay, so now in our equation, in our solution, what we want to do is we want to find the normalization constant. Then and only then we are going to have normalized wave function, radial wave function. Okay, now norm of psi is given as integral psi square d tau, which is equal to 1. Now in our solution there is no complex number and it's a radial wave function, and the normalization condition can be simply written as the integral r is equal to 0 to infinite rnl rho square r square dr is equal to 1. All right. So then rewriting the terms, I will then substituting the terms in, that is the RNL. So we have root to the power 2L into e to the power minus rho, because there is a square over here, right? That's the magic. And then we have the associated Laguerre polynomial, its square r square dr is equal to 1. Okay, so then the terms follows. Now when you are looking at the terms, we know that we are right now in the form of dr, right? Then I can write it in terms of rho, but to do that I know that my rho is equal to alpha into r, right? And rho to the power minus 2 is equal to alpha to the power minus 2, r to the power minus 2, and my r is rho by alpha, and dr can be then written as d rho by alpha. So using all this terminology in this equation, right, we rearrange the terms, we rewrite the terms. Is it clear? All right, then we get, by simplifying from all the above equation and using the generating function of Laguerre's polynomial, finally we get to find the normalization constant. Okay, now associated Laguerre polynomial, it's also a special function. As I have been saying in all the previous lectures of the quantum mechanics, is that the special functions require the entire separate lecture series, right? We cannot discuss in depth what is actually happening, but you can look at the generating function of associated Laguerre's equation to understand how this transformation happens. For the exam point of view, you can remember it for right now, but to understand it, you have to definitely look into the special functions. Moving ahead, so now we have the normalization constant, right? So this is our equation of normalization constant, and from the normalization constant we substitute it in the RNL row, that is this equation. We substitute the value of normalization constant, and the normalized radial wave function is given by this equation. All right. Okay, so this is the derivation of the normalized wave function for hydrogen atom in bound state. Right, now the discussion of bound state can follow, and it's not a complete wave function because we have just calculated a radial part, right. Okay, so if you are interested in the following follow up of this equation and the detailed discussion of the hydrogen atom and the discussion of bound state, let me know in the comment section. Please like this video, share it with your classmates and your friends.